Hello, everyone. So today we're going to give a talk about the so-called Renode Zephyr Dashboard. And we originally submitted the talk where we said we're going to simulate 130 plus platforms, but sadly that's no longer true. We're simulating 170 plus. In between the submission and today, we managed to get 40 more to work. I'll start with something about us, just because yesterday after the keynote, someone asked me, "Oh, so Renode's open source?" I was like, "Oh, is that even like something you have to ask?" So we're a company that only does open source, right? If we're going to talk about something somewhere, it's going to be about our open source engineering services and about our open source tools. So obviously, kind of the things we're going to talk about is all open source stuff. We tend to help people build products. Very often we just, kind of participate in the development of different kind of IoT solutions. But at the same time, because we're kind of open source oriented, we always look at the broader picture, at the tools, at the workflows, try to make sure that things are kind of fundamentally being made in a sound way that's kind of future-proof. And open source, we believe, is the way to do it. And we noticed one of the things that we've created, and the dashboard as well, as part of that philosophy. Just briefly, Renode is a simulator. It's software focused, of course, and hardware agnostic. Software agnostic, so you can run any type of software in it, binary compatible to what you'd normally run on your hardware. And the most important thing to be said about it is that it's a plug-and-play system. So you take your building blocks of a platform, your CPU, your peripherals, your sensors, you connect them up in a configuration-based methodology, and it should work, right? So this plug-and-play nature is kind of one of the most important focuses and has been an enabler for what we're going to talk about today. Essentially, as I mentioned, the important thing for us is as well that we run the same software that you run on hardware. It has to be binary compatible. So we're not trying to do any tricks or hacks or like changes to your software that would enable Renode. Sometimes, of course, when we're developing something, we do that, but then eventually we want to support platforms in a way that the software doesn't really realize that it's running in simulation, right? It's kind of supposed to be one-to-one to what you deploy in production. That aspect is very important for us because it's very testing focused, right? We're kind of looking at CI automation a lot. That's kind of a primary focus for us. So we realize that if you test the real stuff that you deploy, you have a high likelihood that you're going to succeed, versus if you have a special version just for simulation, that kind of smells fishy, right? And of course, Renode has a lot of features, actually to the point where sometimes we have a problem with documenting them all. So sometimes there'll be a feature that kind of exists, but we haven't managed to tell you that it does. We're trying to fix this, of course. How did it really start? So kind of perhaps also good to mention is that it's an old project. We started it out in 2010. And we created it as a tool that was, for ourselves. Like, we really are users of Renode because we never even thought it would be a tool that other people would want to use initially. We quickly saw that, okay, the problem that we're facing, this kind of development of hardware, software for hardware, where reproducibility is a problem, where sharing the hardware is a problem. Nobody heard about the chip shortage at that time, but still having the same, ideally, exactly the same hardware on your table between like 5 teams spread across 3 continents wasn't necessarily simple to do. So we felt, well, simulation is a good solution to that problem. So we built one, and then we realized, okay, it's actually pretty cool. We should share it with the world. And so we ended up open sourcing it and making it into a framework. Originally, Renode was just called Emulator because it wasn't a project. It was like an emulator that we developed, so it was just called Emulator in our internal issue tracker. But of course, we kind of came up with a nice branding and logo for it. And sometimes people are a bit confused because, it looks like a very kind of commercial product, but it is fully an open source framework. And we always laugh that, come and buy Renode Pro, which of course doesn't exist. There's just Renode, the whole framework is
comes on CD only.
Yeah. So when we say it's a Renode Pro feature, it's kind of a joke. All right. How's it work? It's an instruction set simulator, kind of like QEMU. Uses the same principle to translate instructions from the guest to the host. We have, of course, a lot of infrastructure around just the core. The cores are written in C for speed, but then we have a whole framework in C++, C# that takes this to a higher level. Kind of, we have all sorts of components, peripherals, sensors, wireless media, and all sorts of different building blocks you can use to create a simulated, world in a sense, right? But we're not tied to C# in the absolute sense. We can also have peripheral models in Python. We even have been experimenting with Rust and being able to create models in Rust. We have some demos how to do that. So all in all, think of it as a framework. It's not just a tool. It's more of a framework that allows you to seamlessly create simulation solutions. One observation that we've been kind of consistently looking at, and that's since the very beginning, actually the way Renode was born is we were looking at FPGA-based soft core systems and saying, oh, these are like very configurable, and if you want to simulate them, you also have to have like a configurable simulator. And also we were looking at, okay, these systems are actually built from like blocks, and those blocks tend to repeat and repeat and repeat. So it doesn't make sense to try to reflect them in actual code, right? You'd like to have code that models specific IPs and then configuration that connects them together. And that separation between code and configuration has been a driving force for what Renode really is. So we have all of those different peripherals, but they also tend to fall in classes, right? I mean, there are PCIe controllers, there are I2C controllers, and so on. And these also show a lot of kind of similarity between them. So we also created APIs, just like Zephyr, of course, does the same thing, only on the other side. You're looking at all the I2C controllers, and you start seeing patterns, right? So you come up with APIs that abstract out those patterns. And over time, of course, we've built this into a fairly robust framework. I still think there's a lot of work in front of us, just like there's a lot of work in front of Zephyr to kind of uncover all of this stuff. But the key observation in that those IP cores, when you're building a chip, those are being bought from a very limited set of vendors, and that you don't really want to change things too much because like hardware verification is hard, so you're gonna just reuse as much as you can. This observation is kind of cool if you're an operating system builder or a simulation creator, right? Because you can leverage that fact very well. So yeah, an SoC like this one, it might be heterogeneous, it might have different kinds of peripherals, and we would describe those systems in what we call the REPL files, Renode platform files, and those files are the configuration files I told you about. We're going to show them in a second. And then we also have a scripting language of sorts, like this is the same thing as we use in our CLI, and that scripting language just allows you to then kind of do stuff with the simulation, right? So you assemble the platform in a REPL file, you make the simulation run and do stuff, and I don't know, you set up some logging facilities, etc., in the REST files. A lot of people ask about this, like how do we add those things into Renode? How do we work with like new platforms? Basically, we typically just use the documentation and data sheets to drive this, because like if you're writing a driver in Zephyr, you're going to do that. And so we are the other side. We're trying to kind of reflect this API, but on the other side, we're trying to functionally model what the hardware does. We, of course, observe software a lot. We look at what software does. It's a very good kind of guidance. I mean, assuming the software is halfway decent, but Zephyr tends to be, so it's a good kind of way to benchmark what you're doing. And the observation is also that you don't really, like, we're not modeling hardware for hardware developers typically, right? We're trying to model hardware so that we can run software on top of it. And not all of the blocks that are found in the SoC need to be modeled directly. We actually have a lot of ability to mock things, to stub things, to just create little bits of Python code that just return a value and stuff like that. Because at the end of the day, you want to be quick, right? You don't want to be like super accurate all the time. Like sometimes you do, and then you put in the work to do that. But most of the time, you're kind of looking at how do I actually test my software, and this little block in the hardware that's doing this very important but ultimately not important thing, you can just pretend that it's there and just say, oh, I return 0xFFF, right? And done. And this has allowed us to kind of be pretty quick about adding new stuff. So all of this configurability and like the ability to quickly mock things and so on and so on. All these things kind of put together resemble like kind of gave us some cool ideas, right? Some cool concepts. And if you look at specifically, I've been telling you about this in kind of a very theoretical way. On the right, you can see an actual Renode platform file. This is what we'd use as a configuration format to drive this. Obviously, it resembles like device tree or something else a little bit. We've set up our own format just because we felt that we don't typically need as much information, really. We typically need, where the thing is on the bus, what IRQs it has, some other kind of configuration parameters. But ultimately, those files are pretty concise and pretty readable, and you can write them by hand without having to refer to like extra tools that will tell you what to do, or you can change them easily. And this format has kind of served us well for prototyping things and for putting things together. And we also were able to create, automated generators for it. Our original kind of auto-generation capabilities were kind of mostly driven by things like LiteX and generally SOC builders. So if you have a SOC framework that can have like lots of different cores, lots of different peripherals, you don't want to be writing all of those variants by hand. So we created a generator that just reads the LiteX configuration, for example, and outputs the relevant REPL file. But then it also serves us as a base for this work, for the Renode Zephyr Dashboard work, where suddenly we realized, okay, you can actually go and generate this at scale, not just like for one SOC generator, but for all of Zephyr platforms. And OpenTitan is another project that also uses this kind of facility. If you heard about this open silicon security project from Google and others, we're also working with them and generating Renode descriptions. That's the minimal example. If you're kind of wondering how small can I get, like this is a working platform, right? Just a core, your memory, and you're there. Now for RESC itself, RESC is the scripting language. That's what you would do to like, set up the binary and everything else, right? Because that one is for describing hardware. If you want to put software on top of that hardware, you're going to execute a few commands. Not all of these commands are actually necessary, right? So like using sysbus is just like a utility to get sysbus into our namespace, let's say. We're creating a machine, we're loading a platform description from the file we just created, setting up an elf file and a variable, setting up a macro that on every reset we're going to run this elf file. I'm debating actually whether we shouldn't kind of try to get rid of this and make this default, right? Like set.
Let's discuss this after the talk.
And then show an analyzer for UART. So basically open a window and show you characters as the characters appear, or take in your inputs, right? It works both ways. So this is pretty minimal. We can probably make it even shorter, but we have a lot of examples and demos in the framework that you can just rip off from, basically. We're kind of working to improve the documentation of the language itself. And the important thing to say here, perhaps, I think it's probably on the next slide now. This is a reflection of how Renode works internally. So all of those commands are just API commands. Like we have auto, and Peter will show a demo later.
Yep.
We have auto completion and all these things where those commands are kind of just calls to internal functions of Renode. So everything's exposed. We're kind of giving you the full capability to like do anything that the framework allows.
Yeah, this means that, for example, if you have an object that's called machine and the class that is reflected by that object has a method called load platform description that accepts a string parameter.
And the add characters, if you're wondering about this, is just a path, right? So if we want to path the file, the add character just gives you a path. And that's what you normally see when you run Renode. Like you have this CLI, you type those commands and they correspond exactly to the language in the scripts. It's the same thing. And then when you run them, you get a log window. You get, of course, the output from the UART. That's the analyzer, as we call it. And you can see the philosopher demo being executed on the right. Right.
Okay. So as Michael said, when we're modeling our platforms, we very often rely on documentation, but we also want to verify if it works with the software. And we have many demos in Renode. We have demos for Bluetooth. We have demos for Linux being booted by U-boot or OpenSBI. we have a lot of Zephyr demos, we have micro-ROS, we have demos with UIs or just blinking LEDs, which is cool because we can show many different features of Renode, but it doesn't really give us coverage of proper testing, right? So we can't really compare if this platform is better simulated to the other because we have different ways of testing these platforms. So we use different OSs. We have different build systems even for these samples. So we can't really compare if our support for platform X is as good as our support for platform Y. So what we need is a system to verify the same or similar workload on different platforms. And of course, Zephyr gives us exactly that. So it supports a lot of platforms. And it has quite a few demos that we can choose from. Later you will see that we focused on 5 demos for now, but we probably will think about more in future. And the build system is very easy. You all probably know it very well. And it has a lot of structures. So yeah, speaking about build system, if you can build a platform for a sample for a platform with a simple command without having to worry if you have the proper tool chain, etc., that gives you a lot of possibilities because you don't have to spend a lot of work to just build everything for every target. And yeah, this structure is very important for us. One of the most important pieces of information is device trees. And I will show you how we take device trees and transfer them to rep files, but also the YAML description of the specific pieces of hardware, and the structure of the repo itself is sane, right? So you will find things where you expect them to be, which is very important if you want to script things. And what we try to do with our work here is to take this information that describes the software and try to simulate hardware based on that information. So of course, probably everyone is familiar with device trees, so it's an hierarchical and structured information about the hardware platform, describing memory layout, describing interrupts, and some details of the specific platform, which kind of resembles what Michael showed in the rep files. It's of course used by Zephyr, but it's famously used in Linux or U-boot, which are also interesting for us from the automated testing perspective. And we use this, of course, to select specific drivers. If the drivers are being selected for a specific binary, then this binary is going to ask Renode about the specific models. So we will use this information to add these models to the platform description. So this is a sample DTS, which defines a UART, a CPU. This is fairly simple. Of course, they can get very long and complicated. So what is important for us? Of course, the list of devices and the interrupt connections is very important. Information about the types, so the compatible node in the compatible information in specific node. And we will use it to generate a rep files, and I will show it live in a second. So we created a tool. We call it DTS rep, which I believe is pretty self-descriptive. It's of course open source. It's available on our GitHub. And yeah, well, it takes the device tree and gives you a rep file. No surprise there. So how does it work? Michael showed you our platform description, which uses information about types that Renode supports. Of course, these types are not used in device trees. We have information about compatibility with drivers, but we need to have the mapping. There is no way to guess which node from device tree will correspond with which model that we have in Renode if we don't provide this information. So this is actually quite some work to add this mapping, but not that much really. So the amount of drivers is limited, the amount of models supported by Renode is also limited, and we can just create a match combining one and the other. So yeah, we create this JSON file that just gives you the important mapping. We also create additional overlays for specific platforms. So if there is a situation where we lack information in the device tree, or we cannot extract it automatically, we can add a specific additional information for a platform that will augment our rep file, so it's actually usable for simulation. What are the problems with this automatic translation? So first of all, many of the Renode models are configurable. You can decide, okay, so for example, there is let's say a queue in a UART, and it can have a configurable amount of characters. And that's a parameter that you have to provide, and that's not usually extractable from device trees. So we handle this by these overlays, right? So we can decide to augment this platform description with a specific information that will help us create things.
I think there's also some logic in the parser itself, right? So
in what?
In the parser itself, when we encounter specific nodes, we also have some code to augment this.
Yeah,
That's
this is
in the overlays, right?
mostly going to be handled by overlays anyway.
We'll try to move it to overlays anyway.
Yes.
Just mentioning that it's not.
Yes, these are hacks, but we try to get rid of them. There is also a topic of interrupt connections. This can be extracted from device trees. We don't do that yet, but we will. We just didn't manage to finish that before this event. And one of the things that leads us to creating these hacks is that compatible strings are not always fully descriptive. This is especially visible if you're using HALs that have if-def parameters, right? So that's especially visible when we're running, I believe, ST platforms, where you can have the same compatible string for a UART because the API for the HAL is the same. For different platforms, but internally they're absolutely different, and you have to have some additional logic to guess what type of peripheral should be used for a specific platform, because we have different models for different for example, ST UARTs. So when we have the rep file, then we need to generate the RESC file. Thankfully, this RESC Michael presented, so this one is extremely generic. So there is no demo-specific information here. It only loads the ELF file and then also loads the platform description, and that's pretty it. So usually this is enough for us to have a working simulation. Hop. Oh, yeah. So we have a working simulation, but simulation that we can load in Renode, but we don't really know if it really works or not. So we use Robot. Robot Framework is a Python-based tool for testing. It's not ours, but we employ it for Renode, and we create a special integration layer for it. It allows you to write tests, which I'll also show, which are very nice to work with. Yeah, and both can be easily templated, so we can just use a common pattern and then just fill out the specifics. So we can generate them as well. Yeah, and this gives us Zephyr Dashboard, which has 175 passing boards on Hello World example right now. Sorry. So the screenshot is a little bit too old because it actually covers 130 something, but now we are at 175. We can achieve this because we have a lot of models already, but we don't have the platform descriptions. We can generate them from Renode, from Zephyr. When we're running so many demos, we can extract a lot of data from these runs and from the build process and from this whole procedure. And I will show you what kind of data we can see in dashboard and what can we extract in a second. Because we generate a lot of artifacts that we allow you to just download and just run the demo yourself on your local machine. And it also links to Renodepedia, which Michael told about yesterday, and we will gladly show it to you on our booth. Probably not during this talk, but yeah, there's a lot to explore from the dashboard. So this is the link, and let me go to the demo part, as I have a few minutes left. So yeah, let's start with, I hope the console is visible. Let's start with DTS rep. What I need to create rep file, I need well, device tree. The easiest way to get a full device tree, because device trees are included, they can be included one from the other. So to get a full device tree, I have a cheat sheet, not to mistake anything. So I can just build the one of the samples. So let's build this one. And now I can do overlays. I can run DTS rep on the DTS that was created in the build directory, defining that I also want to use specific overlays that we define. And I will show you in a second what's in them. Yeah, and that's quite quick. So I can cut out with rep file. And this is a simple, automatically generated platform description for the platform that I just built. And the overlays part, what it does is DTS rep overlay. For example, for F4 platform, we can load an additional SVD, right, to provide additional logging and things like that. And for V7, we want to define an additional block that is not mentioned in the device tree, but is specific for ARM cores. So this is the information that we just want to add to our platform description. Due to time constraints, I will probably not show you other options of DTS rep, but I wanted to show you the dashboard itself. So yeah, this is the dashboard. We have a lot of platforms that you can scroll through. We have 5 demos: MicroPython, Zierhoffer, Shell, TF Lite Micro. So let me just download artifacts built for Arduino Nano BLE Sense. And let me extract this. And let's show the files in the terminal, because yeah, that's better. So in the artifacts package, we see quite a few things. First of all, we can see the log from building Zephyr. So if something goes wrong, you can easily see what was the problem, right? So of course, this is a standard log that you're pretty familiar with. Thankfully, this one succeeded. We also get the ELF file itself. We also have the SBOM information, 3 files here. And of course, we get the device tree that was generated by DTS rep. We get the config from the specific sample that we built.
The device tree was generated from Zephyr, right? The rep.
Obviously, yeah. So device tree was generated from Zephyr, and the rep file was generated by DTS rep. So we have all the data that is required to run the simulation. So let me open the robot file, for example. So this is a MicroPython example in which I can show you what it does actually in the, let's see the asciinema. Oh, I can play it in the terminal as well. So yeah, I also have the asciinema file that is a recording of the UART output. So it will be this. So you can see it being output live. So you see that we do some crazy mathematical stuff, and we define some functions that are also very advanced, but it works. So of course, what we can test here is that, first of all, the MicroPython works on this platform, that we have UART that is responsive, so we can input data, so we have interrupts working, etc., etc. So there's a lot of information that you can learn from this. And this whole procedure was guided by the robot test. So this is, I'll probably make it a little bit smaller. Yeah. Oh, yeah, I'm finishing right now. So just let me finish this file. So yeah, what you do is you define your test. Sorry for the white space at the end. So you define a test. For example, you wait for a prompt, you write a line to your word, you wait for something to happen, etc., etc. So you create steps that show you what should be done in your test.
There's one question in the Discord.
Yeah.
Any plans to support Renode out of the box on the VS Code extension? For the Nordic team. Okay, so it's an internal question. I'll let Nordic answer that one.
Yeah, that would be great. Okay, so yeah, summing it up. Sorry, we don't want to eat too much of your time. This kind of data allows you to reproduce things locally. We can easily rerun this very same sample on your local machine. So yeah, of course, this will not do the automatic input, etc. But I can do print. Oh, well, I hope I can do print. So yeah, this is it. And this procedure gives us 175 platforms running on Hello World and quite a lot on other samples as well. And we're definitely meaning to move even forward with this. And yeah, I welcome your questions.
Yeah, we can take the questions at the booth as well.
Thank you.
Perhaps there's one. So the question was, can we simulate BLE yet? And the answer is yes.
Yeah, we can simulate BLE. We have a demo that's actually loading scripts, multi-node, NRF 52840 BLE, which runs a central and peripheral HR samples from Renode, from Zephyr. It's still being worked on, so there are some quirks there, but it's pretty operational.
Thank you. Oh, Kumar?
Not only a question before, you mentioned that in the BTS to REPL kind of scripts that you end up having to special case certain things and so forth. I would say that probably a lot of those things we should look at filing bugs because they're things that should be fixed in the BTSs. Because like you gave that, you were an example on STM32. You probably need an additional compatible sort of distinguished event when you guys can see off proper things. So if you guys find things, you could let us know.
Yeah, so the comment was, just to repeat for the sake of streaming, that some of the additional data that we have in DTS to REPL that should probably be actually part of the device trees. And we definitely agree. We do find some parts that we think that should be covered in Zephyr because that would make things more discoverable for everyone, not only for, well, even if the build system will handle things without this information, it will be very beneficial for everyone. And the other thing we are trying to work out is how to automatically find out which driver should correspond to a specific compatible string without having to actually build the software and extract this data afterwards.
Yeah, that's something of interest for a lot of things. So,
Cool. I'm very happy to have that conversation. Thank you. Thanks, guys.
Thank you very much.